Hi everyone, I'm Professor McBain and welcome back to Chem 100. This is the first video in a series about how we can classify matter into elements, compounds, and mixtures. So we're going to start off by defining those things. All right, let's get started talking about elements, compounds, and mixtures, and more specifically, how we classify various types of matter into these categories. You do have some online reading that you need to do to accompany this lecture, so please don't be getting in the habit of only watching the lecture videos. You should also be hopping over to our free online textbook, Atoms First, and you should be reading through section 1.2. So to start things off, let's get you some definitions. So in your book, you should see a page that just says atom, molecule, compound, and it might be blank, and so this is where you get to write it down. So an atom is the smallest particle of an element that still retains the properties of a larger sample of that element, okay? And it cannot be broken down into simpler substances by any chemical changes, okay? And furthermore, the atom, if you also try to break it down into smaller pieces by physical means, then you're going to start losing the properties that a larger sample of that element would have, because you're starting to take apart the atom into its constituent, subatomic particles. All right, moving on. A molecule would be two or more atoms that are joined together by strong forces called bonds. Now, what's interesting about a molecule is that those two atoms can be the same element, say two atoms of hydrogen, or they can be different atoms, different elements altogether, say hydrogen and sulfur, right? And either way, as long as you've got two or more atoms that are bound together, then it's considered a molecule, okay? And then the atoms in that molecule move around as a unit instead of moving around as individuals, okay? So kind of like if you have some keys, right? As soon as you put all of the keys on a key ring, if you throw that whole ring of keys, the whole ring of keys is gonna go together, okay? All right, so now a compound. A compound has to be a molecule or an ionic solid, but either way, you've got multiple atoms bound together. But it's also made up of at least two different types of atoms, two different elements, okay? And they're held together by chemical bonds. And furthermore, a compound can be broken down into simpler substances by chemical changes. So a compound would have to be something like hydrogen and sulfur, or oxygen and hydrogen, all right? If you're just talking about two hydrogen atoms together, then it's not really a compound. Okay. Some more definitions. All right, a pure substance would have to be something that's composed of units that have a single composition, formula, or identity. It's considered one chemical, okay? And so that single chemical can be either single atoms or it can be molecules, and those molecules can be either the same element or they can be a compound. But the whole idea is that you've got one thing with one formula and one identity, okay? And so the presence of a single chemical is what makes it have a uniform composition. Uniform meaning it's the same throughout, composition referring to what is it made up of. And so uniform composition means, well, it's made up of all the same stuff. It's the same throughout. And Freddie agrees with us. So for example, if you've got a tank full of hydrogen gas, then that tank is full of a pure substance. Or say that you've got a thermometer that has only mercury inside of it, then that thermometer has a pure substance inside of it.
Hey folks, we have a guest commentator for the next minute or so of this portion of the lecture, but then he goes away. So feel free to go back and rewatch this minute segment as many times as you need to in order to understand the content. And of course, feel free to email me with clarification questions as much as you need.
Now, in contrast, a mixture is made up of two or more substances, or in other words, two or more chemicals. But somehow those chemicals just mix with each other without being chemically bound to each other. So for example, salt water. Okay, so the water is still made up of hydrogen and oxygen atoms. And then you've got the sodium and chloride from the salt. But the sodium and chloride and the water molecule, they don't bind to each other. They just mix with each other perfectly. On a similar note, cookies, right? So let's say chocolate chip cookies. The chocolate chips and the rest of the cookie stuff, right? They're mixed together, but they don't, everything retains its chemical properties. Now, a mixture can either have uniform composition where it all looks the same throughout, or it can have non-uniform composition where there's some obvious different stuff going on. So let's take a look at the difference between uniform and non-uniform compositions of mixtures. Okay? So heterogeneous mixtures have imperfect mixing going on. We would call that imperfect mixing non-uniform composition. Non-uniform means that for some reason the mixture is not the same throughout the entire sample of substance that you have. Okay? And often you can see the different bits of chemicals that are in that mixture because there are different colors and textures, or there's a very obvious phase boundary or something like this. So let's take a look at two examples. I'd say the first obvious one would be a human. A human is a very obvious heterogeneous mixture. Now, to look at a human, you'd say, well, I don't know, it all looks like the same human to me. Well, yeah, but let's go a little bit smaller, right? So just the difference between a fingernail and the rest of the finger, those are two very different spots in the sample of the human, right? And so then they're not mixed perfectly, and so then you have imperfect mixing. Similarly, when you consider the hair versus the rest of the head, right? If it was a perfect mixture, there would be the same amount of hair throughout the entire human, and you wouldn't be able to tell the difference between where the hair starts and the skin starts, right? Also, if you were to say bisect a human, right, then you could start looking at the different layers that compose a human, right? You would have the skin and the bones and the veins and then the layers of tissue, right? And so then it becomes very, very obvious that throughout the entire human, from top to bottom, inside to out, there are different substances that make up the human, right? So therefore, it's an imperfect mixture because you have those different substances at various spots in that sample, okay? A slightly less obvious one, but still easy to see, would be, say, oil and vinegar, or even just oil and water. So even though they're both liquids, and sometimes they could both be clear liquids, oil and water do not mix. And so instead, if you try to mix oil and water, there's a very obvious chunk of liquid that is oil, and then there's usually a little phase boundary, right? There's a little bubble that you can see, but we call it a phase boundary. And then there's the rest of the other liquid, all right? And so if it were truly a perfectly mixed mixture, then you would not be able to tell where the oil starts and the water begins. But instead, you have these phase boundaries, and you have a very obvious chunk of water and then a very obvious chunk of oil. Here's a less obvious example, and this would be mud, right? This is actually a boiling mud pit in a volcanic region. So you would look at this and you would say, well, the mud looks to be the same throughout, so it's homogeneous, right? Nope. So the deal with this is that if it's the same throughout, then it all needs to be not only the same percentage of stuff per unit of volume, but it also needs to all be in the same phase of matter, right? And now I'm talking about whether it's solid, liquid, or gas. So if it was a perfect mixture, everything would be in liquid phase. But instead with mud, you can actually take a sample of mud from this boiling mud pit, and you could strain it through a filter that's fine enough that it would capture all of the solid particles of mud, and then the liquid water would drip through. Okay, so what's the point of that? Well, then clearly you have a sample of solid that is being suspended by the liquid, and so because you have very, very microscopic parts that are liquid versus solid, it cannot be the same thing throughout. Heterogeneous mixtures, and actually any mixture, can also be categorized and characterized by how you can separate the components of that mixture. So specifically, Heterogeneous mixtures can be separated by simple mechanical methods. And what do I mean by that? Well, here's some examples. So let's look at the examples that we've made, like cookies and rock and sand mixtures or something. You can separate the components of a rock and sand mixture by just picking the rocks out of the sand. And even in grains of sand, right, if you've looked at a sample of sand, like some sand particles are different colors than other sand particles. And so if you are very, very patient, you can just separate the darker ones from the lighter ones. Or with cookies, you can, once your cookies cool down, right, you can pick the chocolate chips out of the rest of the cookie stuff. So with oil and water, you can't really like take a pair of tweezers and pick the oil out of the water, but what you can do is you can suction the top layer off of the bottom layer, right? So maybe you have like a medicine dropper or a turkey baster or something like this. You can still use the fact that you've got two layers in order to separate them from each other. Now, as for our boiling mud pot mixture or any other sort of sample where you've got solids that are suspended in a liquid, you've got two choices. You can either filter the solids out of the liquid with a very, very fine filter, or you can give your mixture some time for the solids to all settle to the bottom of the container. And it should be long enough time that you're left with some sort of see-through liquid on the top. And so then you just pour the liquid off the top and then you're left with solid particles in your container, right? And so then maybe they're still wet, but still you've separated the components of your mixture. So the rules. Let's actually come down here to the bottom first. Whether you're looking at solids or liquids here, if there are very obviously different spots or parts in the sample that you're looking at, then it's a heterogeneous mixture, okay? Now let's consider that you're only looking at a liquid, okay? And if at first you're thinking to yourself it's the same throughout, well, just remember, if you can't see throughout that liquid, then there's solids blocking your view, and therefore it's not a 100% liquid-liquid, and therefore it's a heterogeneous mixture of a solid suspended in that liquid. Now, homogeneous mixtures, it's still technically a mixture, right? So that means that you have multiple chemicals that are hanging out with each other without being chemically bound to each other, okay? But in a homogeneous mixture, they are mixed so perfectly that you cannot see that there are different bits of chemicals together, okay? So they're mixed so perfectly that it almost looks like it's just one thing. However, you know in the back of your head that whatever you're looking at actually is composed of different chemicals. So it often requires a little bit of prior knowledge about what you're considering. So homogeneous mixtures can't be separated by those simple mechanical methods that we just talked about with heterogeneous mixtures. However, they can be separated if you take advantage of the different physical properties of the components that are in that mixture. So in other words, you can make the components undergo physical changes that one component will do, but another component won't. For example, you can take advantage of the components' different melting or boiling points. So back to our favorite saltwater mixture, which I'm going to touch on in just a moment from here. But to separate the components of a saltwater mixture, right, you can't just take your tweezers and pick out the little ions of sodium and chloride, right? So you got to do something else. But knowing that water boils at 100 degrees Celsius, while sodium chloride boils at 1,465 degrees Celsius, well, you can take advantage of those different boiling points. So you can heat your mixture up to 100 degrees Celsius and the water will start boiling, while the sodium chloride, it's not even going to have melted into a liquid at that point. It's just still going to be a solid. So eventually the water will all boil away and salt crystals will be left behind in your pot. So take, for example, ocean water or even just a saltwater mix. Once you mix salt water and give it enough time to actually mix all the way together, it just looks like water, right? It looks like it's the same thing throughout. And you'll actually find that it all tastes like the same amount of salty water. However, you know in the back of your head that you had to take some pure water and you had to mix it with salt, sodium chloride, in order to get that mixture together. Okay? You also know that this is not a new compound because you've still got the properties of the two substances that came together to make this mixture, which you only know because if they had instead formed a new compound, then it wouldn't just taste like salt and water, right? They would have made something entirely new that probably tasted different and probably even looked different. Let's look at some other examples. A lollipop, right? Let's just consider not the stick part, but let's just consider the hard candy, right? So it's a solid, it looks the same throughout, and yet you know in the back of your head that sugar, when it's solid, would just be colorless, right? And so sugar, well, if it's got a color, then there's also got to be some colored compound with it. If it's strawberry flavored, well, then you also know that, well, sugar is not naturally strawberry flavored either, and so then there had to be that additional component in there as well, right? So the lollipop candy is composed of different chemicals, and yet it looks the same throughout. Hence, it is a homogeneous mixture. Same with brass. Now, brass is a little bit more difficult to understand, but one of the things that you should be thinking about is like, well, okay, so I know that brass is kind of a metal, right? But I can't find brass on the periodic table, right? So brass is actually composed of multiple metals that have all been melted and mixed together perfectly so that they all look like the same thing, but it's actually composed of multiple elements. Same with gold, gold rings at least. Did you know that your gold rings are not 100% gold, the element? Often, actually, in all instances concerning jewelry, gold jewelry is mixed with other metals to make the gold basically withstand the test of time and wear a little bit more easily. Without those additional metals, then the gold would start bending and breaking very easily. Okay. Air, let's actually consider this. So air, like we breathe it and we think, oh, it's all the same air throughout, but actually air is a homogeneous mixture as well. It's perfectly mixed, but it actually is composed of nitrogen, oxygen, and some other gases, right? But they're all mixed in so perfectly, at least at our elevation, that we can't tell the difference between the different gases that we are breathing in.
Okay, that's enough for right now. Join me on the next video where we're going to be discussing pure substances, elements, and compounds.